Hi, your 11s, this is Mr. Lim here, and this is our first video of intermolecular forces and shapes of molecules. Let's get started. All right, so we're going to be describing the valence shell electron pair repulsion theory, or the VSEPR. All right, so that's something we're going to learn, and we're going to identify shapes of molecules from electron dot diagrams. So that's going to be fun. So let's get started. All right. So, valence shell electron pair repulsion theory. So, electron dot diagrams can show more than the types of bonds present within a molecule, such as double or triple bonds, but they can also be used to identify the shapes of molecules. All right, so molecules take on different shapes because the pairs of electrons in the valence shell repel each other because they're both negatively charged. Right, and thus the pair of electrons try and move as far away as possible from each other. Right, so this is the valence shell electron pair repulsion theory. So the idea is that we know that positives and negatives attract each other via electrostatic attraction. We know that positives and negatives will repel each other. So the idea is that these electrons, while they're floating around, they're trying to get away from each other as far as possible. But we also remember that these shared electrons, the covalent bonding electrons, they are stuck between the two atoms. So since they're stuck between the two atoms, they're pulling those atoms together, but they're also trying to push away from each other, right? They're kind of stuck in this kind of push and pull, so they have to find a way to distribute them, which maximizes their distance from each other, but minimizes the distance from the atoms that they're putting together, okay? So the movement of these bonding pairs of electrons move the atoms as well, so that they're associated with, right? So certain shapes form due to the repulsion, okay? So let's find out more about that. So let's have a look. To identify the shapes formed, you have to identify the number of regions of negative space around the nuclei of the central atom and the number of non-bonding pairs of electrons. So let's get started into some of these examples and we'll show what we need. So NH3 is the first example, all right? So here we have NH3 with C3 single bonds and those two extra electrons there, okay? So bonding pairs of electrons we'll highlight in red. Here are the bonding pairs of electrons and the non-bonding pairs of electrons. So we would say that this has but what you're going to think about is that we're looking for regions of negative space. Whoops, I don't want that, right? We're looking for regions of negative space. And a region of negative space is any single bond, double bond, triple bond, or non-bonding pair of electrons. All right, so what we would say here is that there are 4 regions of negative space and 1 non-bonding pair. Okay, so 4 regions of negative space with 1 non-bonding pair in that particular diagram of NH3. Okay, you've got the 3 single bonds and the 1 non-bonding making 4, and then 1 of them is non-bonding. Okay, let's try something else. Let's try CH4. Okay, so CH4, 4 single bonds with the hydrogens around it. Okay, so methane. Okay, so let's have a look. How many regions of negative space? Again, there's going to be 4, and 1 of them is going to be a non-bonding pair. Oops, I didn't want that. Okay, so, whoops, 4 regions of negative space, and none of them are non-bonding pairs. Okay, so it might be better to see this one as another region of negative space. It just happens to be a non-bonding pair. Okay, let's have a look at it, something different. Let's look at CH2O. So CH2O, which means that I'm going to have the double bond to that O there. Okay, so that's CH2O. Now let's have a think. How many regions of negative space do I have here? I've got around the central atom. For this one here, we're going to call the carbon the central atom because it's connected to the other elements. 1 region of negative space, 2 regions of negative space, 3 regions of negative space. Okay, so that double bond counts as 1 region of negative space because those electrons are all going to be kind of clustered around the carbon and the oxygen atom. Okay, and so therefore there are 3, this one here, 3 regions of negative space and 0 non-bonding pairs. Okay, one last example. Let's do H2S. Let's do the H here, the S here, another H. Remembering that S has 6 valence electrons, so we could draw another 4 more here. So how many regions of negative space? Well, there's going to be 1, 2, 3, 4. 2 of them just happen to be non-bonding pairs. Okay, 2 of them are non-bonding pairs. So we identify the regions of negative space and non-bonding pairs. Once we've identified the regions of negative space and non-bonding pairs, we can look at the shapes of molecules. Okay, so if you use this table here, right, this table here, you'll be able to work out what shapes things are. And I might go into class and show the shapes of these when we get to a particular lesson, right? But the idea is that these names of shapes, so linear, okay, V-shaped, pyramidal, tetrahedral, and trigonal planar, are the 5 major shapes that you can have, or the 5 shapes that you can have. And they all are based on some combination of regions of negative space and non-bonding pairs. Okay, so let's have a look here. All right, if we look at this one here, the CH2O, it has 3 regions of negative space and 0 non-bonding pairs. So 3 regions of negative space, that's this one here, or this one here, or this one here, with 0 non-bonding pairs, right? That means it's the trigonal planar, okay? Trigonal planar, and we'll go into class to see what those look like, right? But effectively, trigonal planar is a 3 in a flat, 3 atoms around the central atom in a flat triangle. So planar means kind of flat, trigonal, triagonal, right? Let's have a look at another one of these, okay? So one of the other examples that we drew was the NH3, okay? So the NH3, this one here, 4 regions of negative space with 1 non-bonding pair. Which one is that? That is the pyramidal, okay? What that looks like is an N like a pyramid with the 3 H's on the bottom and the non-bonding pair at the top. Okay, so if you think of a triangular pyramid, right? The N up here and the H's down the bottom. Okay, so that is a pyramidal shape. Okay, we can look at the other ones here. Let's have a look at this one here, the H2S. For H2S, how many regions of negative space did we say it had? It has 4 regions of negative space, remember? Like the non-bonding pairs also count as regions of negative space with 2 non-bonding pairs. Okay, what shape is that? 4 regions of negative space with 2 non-bonding pairs, that's V-shaped. All right, and V-shaped effectively means that it looks like this. There's S with 1 H there, 1 H there, and the other ones are over here. Okay, so that's why you'll see water molecules often drawn in this arrangement, okay, in a V-shaped arrangement, where these are the hydrogens, because that's the actual shape of the water molecule. Okay, couple of other ones. Let's do HCN while we're here. Okay, so HCN, hydrogen, single bonded to a carbon, triple bonded to a nitrogen. Okay, so you'll have to go back through and remember all of your electron dot diagram steps and stuff, but this is just from memory for me. You'll have to go through all of the normal steps to work out the electron dot diagram. But here we have how many regions of negative space? Around the central atom, we have 2 regions of negative space. How many of them are non-bonding? None of them are non-bonding. Okay, so this non-bonding pair isn't around the central atom. So this one here is a non-bonding pair, but it's not around the central atom. So 2 regions of negative space, 0 non-bonding pairs, makes it a linear substance. Linear. Effectively, it makes a line. And if you think about it, these electrons and these electrons here are trying to get as far away from each other as possible. So they're going to be on opposite sides of this carbon. All right, HNO, let's do HNO, N with the H, N with the O, and then another non-bonding pair there. How many regions of negative space? 3. How many of them are non-bonding? 1. Okay, and that's going to be 3 and 1. That's also going to be V-shaped as well. Right, the one we haven't talked about is tetrahedral, right, which is the one with CH4. So CH4. Okay, what does that look like? Again, imagine the triangular pyramid, but instead, you can imagine something sticking out of it as well. The carbon is in the middle, and the hydrogens are as far away apart from each other as possible. All right, so we have a video here. Let's see if this works. All right, where you can see the different shapes, and I'm just going to talk over it. Okay, so you can see this is a V-shaped. Okay, so if this is in 3 dimensionals, you can see that the mouse is moving it around. Okay, so you can see that the central atom here, it's not a good color to put my laser pointer in. Let's do this one. You can see that this is the central atom. Okay, now we're moving on to the pyramidal central atom with the 3 hydrogens. So this might be like the NH3. Okay, this one here is the pyramidal one. Okay, sorry, the tetrahedral. 1 central one, and then 1, 2, 3 at the bottom, and then 1 pointing up at the top. But remember, they're trying to get as far away from each other as possible. And so this one here is as far away as possible in 3 dimensions as you can get. This is another tetrahedral one, where you've got 1, 2, 3 of these as far away as possible from each other, but then this is a different type of atom, right? This might be CH3Cl, right? And then this is a trigonal planar. Right, this might be something like boron trifluoride, boron in the middle, non-octet rule element, 3 fluorines. They've only got the 3 single bonds with no non-bonding pairs, and so they're just trying to get as far away as possible from each other as they can. All right, so they're just going to make a flat as far away as possible from each other. All right, this is more like the CH2O, C in the middle, single bonded oxygens, and the double bonded to the single bonded hydrogens bonded to the oxygen there, right? Trying to get as far away as possible from each other. Okay, this is a bit of cis-trans geometric isomerism. So you'll see, can I pause this video? No, I don't think I can, right? You can see that this one here is the double bond. Okay, that was the cis isomerism. This is the trans isomerism, where they are, this is a trigonal planar arrangement here and here, tetrahedral arrangements there, right? Tetrahedral arrangement around this one here, and then a V-shape arrangement around that one there. Okay, so V-shaped here, with the oxygen with 2 non-bonding pairs over here, and then tetrahedral arrangement over here. Okay, 1, 2, 3, and this one here makes it the 4. Okay, so those are what those shapes are, and I'll probably go look at this in class, but that gives you an idea of what they are. Okay, adios.